Now, compared to room-sized cyclotrons, super colliders are huge, miles in diameter, and they're used to smash atoms into little bits and pieces and then to examine their parts. In Europe, a successful collaboration between 100 countries created the Large Hadron Collider, now the world's largest accelerator. It lies beneath the border between Switzerland and France and is scheduled to be fully operational soon, barring any further technical problems. It is the largest and most complex machine ever constructed at an estimated final cost of $6 to $7 billion. The organization responsible for the Large Hadron Collider is CERN, a French acronym for the European Council for Nuclear Research. In this 3-minute animation, CERN gives the most concise explanation of how the LHC works.
Insignificant though this bottle of compressed hydrogen gas looks, it marks the beginning of the world's largest and most powerful particle accelerator chain, culminating in CERN's spectacular Large Hadron Collider. Hydrogen atoms from this gas cylinder are fed at a precisely controlled rate into the source chamber of a linear accelerator, CERN's LINAC-2, where their electrons are stripped off to leave hydrogen nuclei. These are protons and have a positive charge, enabling them to be accelerated by an electric field. Their journey to eventually take part in ultra-high energy collisions can now begin. This initial acceleration has caused LINAC-2 to be likened to the lumbering first stage of a huge rocket. By the time this packet of protons leaves LINAC-2, it'll be travelling at 1/3 the speed of light. It's about to enter the booster, stage 2 of the rocket if you will. In order to maximise the intensity of the beam, the packet is divided up into 4, one for each of the booster's rings. Straight acceleration is now impractical, and the booster is circular, 157 metres in circumference. In order to accelerate the packets, they are repeatedly circulated, and the electric field is now pulsed, in the same way that you push a child on a swing each time they reach a certain point. Magnets exert a force on the passing protons at right angles to their direction of motion, and so powerful electromagnets are used to bend the beam of protons round the circle. The booster accelerates the protons up to 91.6% of the speed of light and squeezes them closer together. Recombining the packet from the 4 rings, it's then flung on into the proton synchrotron, by analogy stage 3 of our rocket. Let's just follow 2 such proton packets. The proton synchrotron is 628 metres in circumference, and they circulate for 1.2 seconds, reaching over 99.9% of the velocity of light. It's here that the point of transition is reached, a point where the energy added to the protons by the pulsating electric field cannot translate into increased velocity, as they're already approaching the limiting speed of light. Instead, the added energy manifests itself as increasing mass of the protons. In short, the protons can't go faster, so they get heavier. The microscopic kinetic energy of each proton is measured in units called electron volts, and now the energy of each proton has risen to 25 giga-electron volts, or GeV. The protons are now 25 times heavier than they are at rest. The packets of protons are now channeled into stage 4, the superproton synchrotron, a huge ring 7 kilometers in circumference, designed specifically to accept protons at this energy and increase it to 450 GeV. Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large Hadron Collider, or LHC, which lies between the Jura Mountains and the Alps, and straddles both France and Switzerland. Lying deep underground, it has a circumference of 27 kilometers. There are two vacuum pipes within the LHC containing proton beams travelling in opposite directions. Using ultra-sophisticated kickers to synchronise incoming packets with those already circulating, one vacuum pipe has injected into it protons which will circulate clockwise, and the other protons which will circulate anti-clockwise. The counter-rotating beams cross over in the 4 detector caverns, where they can be made to collide. The energy of the collision is double that of the individual opposing protons, and it's the debris from these collisions that is tracked in the detectors. For half an hour, the SPS injects protons. Finally, there are 2,808 packets. During this time, the LHC adds extra energy to each proton, whose velocity is now so near the speed of light that it goes round the 27-kilometre ring over 11,000 times each second, getting a boost of energy at each revolution from the pulsed electric field. Finally, each proton has an energy of 7 tera electron volts, and they're 7,000 times heavier than at rest. The magnetic force needed to keep the beams bending to the ring is so enormous that nearly 12,000 amps must flow through its electromagnets. This is achieved by making the LHC colder than outer space, so that its magnets become superconducting. Now the protons are ready to collide in the detectors. A steering magnet finally brings them onto a collision course.
These multi-story camera detectors record the resulting particle tracks. And they are analyzed by huge supercomputers. The objective is to give insight into the laws of how the universe might be designed. And what have they found so far? We thought atoms were indivisible, but no. Atoms are made up of electrons and a nucleus. We thought the nucleus was indivisible, but no. The nucleus is made up of protons and neutrons. We thought that protons and neutrons were indivisible, but no. Supercolliders have smashed protons and neutrons and discovered that they are made up of smaller particles called quarks. They were named quarks by this physicist, Murray Gell-Mann. Gell-Mann named the particles, and I'm not making this up, after the sound that a duck makes. And he was going to spell it quark, but later found the word quark in one of his favorite novels, Finnegan's Wake. 6 quarks have been discovered, and they are called flavors. And if that isn't odd enough, each of these 6 quark flavors are officially named up, down, top, bottom, strange, and charm. Who says physicists don't have a sense of humor? A proton is actually made of 2 up quarks and 1 down quark. They've also identified subatomic particles they call leptons, and an electron is a type of lepton. All in all, there are only 12 fundamental particles, and then only 4 are needed for physicists to describe every known bit of matter in the world. The up and down quark, which makes protons and neutrons, the electron, and an odd particle called the electron neutrino. Together, these particles and the theories of how they work are called the Standard Model. There's hundreds of different kinds of subatomic particles within these categories, just like there's hundreds of different kinds of marbles. And these are the kind of particles the Large Hadron Collider finds. A hadron, by the way, is the umbrella name for most of the parts in the nucleus, the protons and neutrons. And do we think that these subatomic particles are indivisible? Oh no. There's a whole list of hypothetical particles they are looking for, including charginos, gluinos, winos, binos, and xenos. sleptons, gravitons, magnetic photons, and squarks. And there is some evidence for the existence of antimatter or antiparticles, but this is getting beyond our scope here. Back to accelerators. Besides the Large Hadron Collider in Europe, which is the largest, there are many other particle accelerators around the world. The Fermi National Accelerator Lab near Chicago, the Cornell Electron Storage Ring in upstate New York, which is buried 40 feet under the football field in the campus, the Brookhaven National Laboratory, also in New York, the Stanford Linear Accelerator Center near San Francisco, not all accelerators go in a circle, and the German Electron Synchrotron in Hamburg, Germany. But one more thing. We mentioned that all the weight, the mass, the stuff of an atom is in the nucleus. But after trillions of collisions, not one particle has been found that contains all the mass. It's as if the whole weighs something, but all the particles and the pieces weigh nothing. It's a great mystery in physics today, and the search for where all the mass of the universe is hidden is probably the greatest prize sought out by particle physicists today. The first supercolliders required a massive computing power network that eventually turned into what we know as the World Wide Web. The web was the first tangible, publicly recognizable benefit from collider work. Likewise, the new supercolliders have over 40,000 gigabytes of information pouring out of them every day when they're up and running. So, to handle this unbelievable information deluge, a new network has developed called the grid. Running at speeds 10,000 times faster than our typical high-speed internet connections, the grid could soon make today's internet completely obsolete. The bottom line for nearly all nuclear physics research is energy, either in weapons or in commercial production. This is where the greatest return on investment is. But controlling energy isn't the only reason for doing nuclear research. Curiosity is another. Some scientists simply want to find more and more particles that make up the atom. Others want to understand what the universe possibly looked like at the moment of creation. And still others want to do research into the possible existence and nature of exotic particles and ideas like antimatter and dark matter. It's inevitable that we want to take things apart to find out what makes the universe tick, how the designer built the machine. But the treasures are not yielding themselves easily. Ultimately, it is requiring better, faster, and more expensive accelerators. And the idea of selling multi-billion-dollar experiments with no guarantee of a tangible return is not an easy sell to governments. Case in point is the superconducting supercollider in Texas. The SSC was going to be the biggest accelerator ever. But 14 miles of tunnels and $2 billion later, the project was canceled due to cost overruns and no perceptible return on the investment. The property and the tunnels sit abandoned, waiting for some future use. There are generally three drivers that motivate governments to spend money on really expensive experiments. One is war or conquest, the drive to conquer and the need to defend against conquerors. Thus, you have the Manhattan Project, to be first in World War II to make an atom bomb. Or the race to be the first to the moon to gain superiority in space. Nations spend lots of money on war and defense. The second drive is the promise of economic gain. So, you invest in new energy, or you look for new medicines, or plastics, or post-it notes, something that you think will return money on your investment, and hopefully, big money. And the third motivating drive to spend money on big projects is to have the praise of kings or the praise from God. This will drive people and governments to build big pyramids, cathedrals, and to make great sacrifices. Super colliders are fascinating machines, and without them, our insight into the nature of the atom would be limited, to say the least. But without one of these primary drives, it is very difficult to invest or to sustain the investment in a very costly project. The romance to satisfy our craving for knowledge and adventure or uncovering universal secrets will only take investors so far. Until science can reach one of these motivators, the funding of super colliders will continue to be a struggle. Now, aside from nuclear research and super colliders, here are a few more areas where research and development are extending the frontiers of chemistry. Nanotechnology is controlling matter at the atom or molecule level. A nano is exceedingly small, 1/1000th of a meter. The largest atom is only 1/2 of a nanometer in diameter. So, like an atom, a nanometer is to this yardstick as a marble is to the entire Earth. Really, 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 really small. Notice this is not just miniaturization. In the section on quantum mechanics, we discussed that at the atom level, the laws of quantum mechanics take over and change the mechanical laws. At this micro level, many materials display unique or unexpected characteristics, like some suddenly become electrically conductive, or they resist heat, or accept heat more readily. Some change their mechanical properties and suddenly become more slippery. Nanotechnology taps into these unique characteristics to make new materials. At the atom level, elements tend to behave so oddly, it's almost like getting a whole new periodic table of the elements. Research has been going on for decades, and most of the current work is in making nanoparticles. Fabric manufacturers are embedding super slippery silicon nanoparticles to create clothing that is so water and stain proof you could soak your shirt in a bucket of water for weeks and it would come out bone dry. Nanocomposite plastics are making their way into automobile steps and bumpers. Sunscreens using nanoparticles of zinc oxide that are extremely effective in absorbing UV light. Organic Light Emitting Device, OLED, or OLED, is emerging as the leading technology for flat, flexible displays. It's basically a thin, lightable organic film pressed between two transparent electrodes. OLEDs are showing up in cell phones and MP3 players and are less than 1/4 of an inch thick. With bright, vivid, and detailed images in a short time, OLED technology may be virtually the only display technology on the market. OLED displays will also mean a nearly 100% efficient flat panel lighting, transparent glass by day, and a light source at night. Nokia Research Center, in collaboration with the Cambridge Nanoscience Center, are conducting research into nanoscale communication technologies. Nanotechnology with over 10,000 transistors that would fit on a single fly hair. Nanosensors could detect chemical compounds in food, and in the air. Living nanograss embedded in devices to harvest solar energy, powering electronics, or even entire office buildings. Nanoelectronics that are transparent to the human eye. Surface buttons that become real 3D forms when needed, and then flat again. And wearable devices. Taking a picture of the handbag allows the user to turn the device into a coordinated piece of jewelry. Nearly 1,000 consumer products are currently produced using nanotechnology. These modest, fairly low-tech applications are just the beginning of what could be a new technological revolution. Now, that's all in the consumer products category. At the more science fiction end of the spectrum is molecular manufacturing, building machines and mechanisms with nanoscale dimensions. Super small bacteria-sized computers, or supercomputers the size of a sugar cube with the computing power of 1 billion home computers. Nanorobots that would be self-sufficient microscopic laboratories traveling in blood vessels to perform medical analysis and procedures. The military has invested millions on nano-based research. Microscopic magnetic particles that can instantly line up, turning soft, comfortable fabric into durable body armor at the flip of a switch. You can get an idea of this technology using iron filings in vegetable oil. When you mix iron filings and vegetable oil, it behaves like an ordinary liquid. You can stir it and you can pour it. But when a strong magnet is applied, it becomes more like a solid. You can't stir it. It's tough and resilient. The iron filings line up with the magnetic field and form a solid. Embedded in clothing, for example, the potential for armor or bomb blankets or guard uniforms becomes promising. Another area of investigation is electronic textiles. With millions of nano cameras embedded in the fabric in the back, projecting the image to millions of nano monitors in the front, effectively making the wearer invisible. Private companies and universities are investing billions of dollars annually in nanotechnology research, and the anticipated payoff for much of this research is anticipated within the next 10 to 15 years. Related to the magnetic fluids are shear thickening fluids. In physics, shear means a strain or a stress placed on something. And a shear thickening fluid is a liquid that behaves like a solid when it encounters shear or stress. The most common shear thickening fluid is one you've probably encountered many times in the kitchen. Take a box of cornstarch and add water until you get the consistency of honey. Your goal is to create a mixture that feels like a stiff liquid when you stir it slowly, but feels like a solid when you tap on it quickly with your finger or a spoon. The cornstarch is suspended in the water, and when pressure is applied by hitting it or squeezing it, it instantly forces the long cornstarch molecules together, and they trap the water, forming a semi-solid. Without the pressure, the molecules relax, and the cornstarch flows again. Inserting a spoon leaves it in the liquid state, but jerking the spoon out again triggers the temporary solid state. These liquids are sometimes called non-Newtonian fluids, fluids that change when stress is applied to them. This is in contrast to a Newtonian fluid, a fluid that doesn't change when stress is applied, like water, for example. The ice pick on the right pierced normal Kevlar, but when the Kevlar was soaked in non-Newtonian shear thickening fluid, the pick could not penetrate it. Here, a soft lead projectile penetrates 3 layers of normal nylon. And here is the same nylon treated with a shear thickening fluid. It suddenly becomes tense, flattens the lead bullet, and stops it from penetrating. Though not yet ready for the combat field, the primary potential with these fluids is in military and police body armor, like the magnetic fluid we saw earlier. But this liquid body armor requires no electricity and no switch to activate it. When struck by a bullet, fragment, or sharp weapon, it becomes instantly rigid. By the way, do not put this non-Newtonian fluid down the drain. It will settle in the bottom of the trap, solidify, and block the drain. Then there's superfluids. Superfluids are fluids that seem to defy the laws of gravity and physics. As helium is cooled, it boils until at about a minus 270 degrees Celsius, it suddenly stops and becomes still. It turns into a superfluid. Now, normally, glass can hold liquid helium, but as a superfluid or superliquid, it leaks through the glass. This supercool liquid helium is actually dripping because it has become nearly frictionless. Here, the liquid is defying gravity, actually climbing out of this container and dripping below. It is virtually a fifth state of matter next to solid, liquid, gas, and plasma. The most prominent scientific journal, Nature, published an article in February 1999 that using super cold superfluids, physicists have slowed the speed of light from 186,000 miles per second down to the speed of your car in town, 38 miles per hour. And they are working on slowing light to literally a baby's crawl of 120 feet per hour, all by passing light through a super cold superfluid. A related field is superconductors. At super cold temperatures, some elements effortlessly conduct electricity with no resistance and no heat waste, making them the closest thing in nature to a perpetual motion machine. Plus, they perfectly repel a magnetic field. Here, a magnet sits on a black superconductor alloy of yttrium, barium, and copper. Now, there is no visible magnetic properties in this alloy metal. But pour liquid nitrogen on it, cooling it down to about a minus 320 degrees Fahrenheit. Now, when the magnet is placed over the superconductor, levitation. When the magnet is pushed, the levitation is completely stable, a perfect magnet. When spun, the magnet rotates with almost zero friction, an idea useful in flywheel applications for energy storage. When the superconductor is removed from the liquid nitrogen, it warms past the critical temperature. The magnet slowly lands and the levitation properties disappear. If room temperature superconductors are ever invented, then magnetic transportation, zero loss power transmission, and power storage devices could revolutionize the use of electricity in everyday life. Read virtually anything today on the future applications of chemistry, and you will inevitably come across this word, green. Here's a sample. You can't do green design without green materials, and green material innovations tend to come from green chemists. The future is going to be challenging. We need to save resources and energy, to protect the climate, and at the same time improve our quality of life. In order to achieve all this, we need new technologies for more efficient manufacturing techniques and better products. Green is the modern term for what used to be called the ecology movement, or the environmental movement, or political ecology. It places a high value on international involvement on how resources should be allocated and used at the local level. Commonly associated with the green movement are political, moral, and religious plans regarding civil liberties, social equality, and other ideas of how society should work. For some, even the word chemical is linked to environmental pollution and toxins. As a result, current research in chemistry leans toward energy systems that can supplement or even someday replace our need for coal, oil, natural gas, and nuclear energy. Developing greener plastics from food sources like corn or potato starch, developing products that degrade quickly after use, and increasing the recycled content of new products. Regardless of your opinion of the green movement and any associated beliefs, the ideas of political ecology will continue to dominate two main areas: where the funding for future chemistry research goes, and secondly, what ideas will be considered important for any future work in this field. Einstein said that science is a wonderful thing, if one does not have to earn one's living from it. But lots of people do earn their living from science, because chemistry is big business. A $3 trillion a year business. Chemistry is central to the modern world economy, converting raw materials into tens of thousands of different products, with new ones made or in development every year, coming at us almost faster than we can catch up with it. In fact, it was Isaac Asimov who said, "The saddest aspect of life right now is that science gathers knowledge faster than society gathers wisdom." As a result, the exponential growth of these products always brings concern. Many new technologies generate visions of what might happen if the technology gets out of control. Clouds of self-replicating runaway nanobots that reduce entire cities to gray nano ash. Or biological chemical cures that mutate into unstoppable biological weapons. The concept of a technological superintelligence, a smarter-than-human technology capable of making itself smarter until it becomes self-aware, a scenario often called the singularity. The singularity scenario provides the storyline for countless science fiction films where artificial intelligence perceives mankind as the great threat. On the other hand, many see technology as having an overall beneficial result for society. The alchemists failed to find a way of changing ordinary metal into gold, but through their failure, modern chemistry was born, which has since produced new metals, colorful dyes, plastics, foods, synthetic fibers, and antibiotics. And who knows what beneficial discoveries are just around the corner? Instant pain relief drugs, instant water purification, bionic limbs. In computers, what used to fit into a building now fits in your pocket. And what fits inside your pocket today will fit inside a blood cell in 25 years. While virtually any of these scenarios is possible, the near future is probably a bit more modest than what we see in the movies. Accurate predictions are nearly impossible, and factoring in the unknown is very difficult because it's unknown. For example, war shows up at the most inconvenient times, disrupting some research and accidentally creating entirely new ones. And many events are just simply beyond our ability to predict or control. It's pretty tough to factor in that kind of a situation into your research grant. It's also completely possible that technology will level off, reaching a plateau that may take centuries to advance beyond. And advancements usually take billions or trillions of investment dollars. Our anti-gravity research money often gets funneled off just to pay the laboratory light bill. And when it comes to investment dollars, societies make choices. Like last year, people spent over $500 million on ringtones for their cell phones, over $4 billion on energy drinks, $11 billion at amusement parks, and another $11 billion on bottled water. There you go. With that kind of a technological investment strategy, in 15 years, we will definitely see an exciting new roller coaster long before we see any breakthrough in cold fusion, because societies make choices. G.K. Chesterton observed that all science is a detective story, not to find out why some man is dead, but to discover the darker secret of why man is alive. Thus, the ultimate objective of science is to bring us to a closer understanding of ourselves and to the one who gives humanity its ultimate purpose and meaning. The father of modern chemistry, Robert Boyle, the man who separated alchemy from science, summed it up this way: "When with bold telescopes I survey the old and newly discovered stars and planets, and when with excellent microscopes I discern the inimitable subtlety of nature's curious workmanship, and when, in a word, by the help of anatomical knives and the light of chemical furnaces, I study the book of nature, I find myself ofttimes reduced to exclaim with the psalmist, 'How manifold are thy works, O Lord! In wisdom hast thou made them all.'"